When we look up at the night sky, we are seeing only a sliver of reality. The rainbow of colors our human eyes can process, visible light, makes up a microscopic fraction of the total electromagnetic spectrum. This biological limit hides a vast amount of cosmic information. Space is filled with dense, swirling clouds of dust and gas that physically block visible light waves, keeping the universe's most important structures obscured. To bridge this gap, NASA spent 25 years and $10 billion developing the James Webb Space Telescope. Its massive 705-kilogram array of gold hexagonal mirrors is designed to catch faint infrared light, longer wavelengths that pass through barriers that visible light cannot. Detecting that invisible light requires extreme thermal stability. The telescope sits at the L2 point, 1.5 million kilometers from Earth. Hidden behind a sunshield the size of a tennis court, it operates at minus 266.75 degrees Celsius, just a few degrees above absolute zero. This deep freeze location is a departure from previous missions. While the Hubble Space Telescope operates by orbiting directly above Earth's atmosphere, Webb orbits the Sun, remaining in Earth's shadow to prevent any heat from its own electronics or the planet from drowning out the faint signals of the deep past. Webb operates as a high-precision sensor, translating raw infrared frequencies into a detailed map of a universe that was previously inaccessible to human sight. The core physical advantage of infrared light is its wavelength. Because infrared waves are much longer than visible light waves, they can slip right through dense physical barriers like cosmic dust clouds without being absorbed or scattered. We saw this physics in action when the telescope pointed its cameras at the Southern Ring Nebula. The initial images captured a massive, swishing cloud of planetary gas being expelled by a dying star. When researchers switched to the telescope's MIRI camera, which captures even longer infrared wavelengths, the view pierced through those thick dust clouds. This revealed a second, dimmer star at the center of the nebula, which had been completely hidden behind the gas. This same penetrating power allows us to observe the birth of stars. Looking at the cosmic cliffs of the Carina Nebula, the infrared sensors cut through the haze to reveal bright red dots. These are infant stars forming inside the dust, objects that remain invisible in standard light photographs. Webb also sees into the past using gravitational lensing. Massive galaxy clusters like SMAC's 0723 exert such a strong gravitational pull that they warp the fabric of space. This creates a natural magnifying glass, bending and amplifying the light from galaxies located directly behind the cluster. As the universe expands, the space between us and distant galaxies physically stretches the light waves traveling through it. This process, called redshift, shifts the light toward the red end of the spectrum. The more red a galaxy appears, the more space it has traveled through, allowing scientists to use color as a precise measurement of age and distance. By looking through dense cosmic dust and reading these red-shifted signals, Webb provides a physical record of light that has been traveling for over 13 billion years. Beyond visual imagery, the telescope analyzes the specific properties of the light waves themselves to determine what distant objects are made of. This process relies on how materials interact with light. For example, a leaf appears green because chlorophyll absorbs red and blue light waves while reflecting the green wavelength back to our eyes. In space, we look at this in reverse. When starlight passes through the atmosphere of a distant exoplanet, specific wavelengths are blocked by specific molecules in the air. When we measure the light on the other side, we see dark gaps where those specific colors were absorbed. Using its NIRIS instrument, Webb stared at the exoplanet WASP-96b for 6.5 hours, recording the exact wavelengths of light that were missing after passing through the planet's atmosphere. This data graph charts the amount of light blocked across various wavelengths. The distinct dips in the data match the known absorption pattern of water. By identifying this specific barcode of missing light, scientists proved the presence of H2O in an atmosphere 1,150 light-years away. This allows us to verify the chemical makeup of distant worlds without ever needing a direct, high-resolution photograph of the planet's surface. While finding water is a major milestone, it does not automatically indicate life. WASP-96b is a gas giant with a surface temperature over 530 degrees Celsius, a volatile environment far too hot for any known biological organism. To find life, we look for planets that meet a specific set of physical requirements: a solid rocky surface and a temperature within the habitable zone, where liquid water can exist without boiling or freezing. These criteria lead scientists to a target called TRAPPIST-1e. Located 40 light-years away, it is one of the most promising candidates for a habitable world. TRAPPIST-1e orbits an ultra-cool dwarf star. Because this star is much cooler than our Sun, the planet's close proximity allows it to stay within a temperature range that could support a stable atmosphere and liquid oceans. Its physical dimensions are also remarkably similar to Earth's. It possesses a confirmed solid surface, and its radius is 91% the size of our own planet. Webb's next mission is to scan TRAPPIST-1e's atmosphere specifically for a combination of carbon dioxide, methane, and water vapor. On Earth, these gases exist together because of biological processes. Finding this specific mixture on TRAPPIST-1e would be strong evidence of a living ecosystem. By measuring the gaps in light traveling across the void, Webb allows us to peer into the chemical makeup of distant worlds, potentially bringing us closer to answering if we are alone in the universe.